What if the key to building truly generalizable robots isn't teaching them to understand the world, but to, well, imagine it? Today we are diving into a paper that really changes the conversation around robotic generalization. It's called VideoVLA. Video generators can be generalizable robot manipulators.
And it tackles a huge problem. I mean, traditional vision language action models, VLA models, they still really struggle with generalization. Even the big ones built on these massive pre-trained understanding models.
Right, they can't handle novel objects or unseen tasks very well. So VideoVLA proposes a complete paradigm shift.
They leverage a massive pre-trained video generation model, specifically a diffusion transformer based on CogVideoX 5B. The idea is to pivot robot learning away from just perception and towards something more generative and predictive.
And the way they do that is with this core innovation, a dual prediction strategy.
Yeah, that's the heart of it. The model jointly predicts two things: the next sequence of actions for the robot, and it generates what they call a visual imagination, basically a future video clip showing what should happen if those actions are correct.
And the key insight, which they prove out, is that the quality of that imagination, how physically plausible it is, strongly correlates with whether the action will actually succeed.
The results really do speak for themselves. VideoVLA gets state-of-the-art generalization. It shows this robust skill transfer between different robot bodies and, mastery over novel objects.
That's that 65.2% average success rate on picking up objects the robot has never seen before in simulation.
Exactly. That's a huge number.
So 65.2% on objects like a wrench or a flashlight, not just a simple block. That's a massive deal. What was it about the previous VLA models that made this so hard?
It's just a totally different way of thinking. For years, the goal in robotics, the kind of white whale, has been generalization, getting robots to adapt, pushing towards AGI. But models built on just understanding the world kept hitting a wall.
So if the old models just knew what an object was, this new model is trying to learn the actual physics engine of the interaction itself. Why did those comprehension-focused models fail to adapt?
Well, the current VLA models, things like the RT series or models like Octo, they're really optimized for perception. They're trained to map an image and a text command to an action.
Okay.
But that mapping is brittle. It doesn't automatically give you the ability to anticipate what happens when you interact with something totally new, when the physics of it are different than what you've seen.
That's the gap right there, the gap between knowing what a wrench is and predicting how it's going to, say, roll or pivot when you try to grip it.
Yep.
And that's where VideoVLA gets its inspiration.
Exactly. The authors looked at these huge video generation models, things that can create super realistic video from a text prompt. And these models already have incredible generalization and a really impressive sense of physical plausibility.
They just learn it from watching, millions of videos of the real world.
Right. They have this inherent planning capability built in. They know how the world is supposed to look frame to frame.
So the big question, the paradigm shift, is this. Can we stop trying to tweak these perception models and instead just adapt a video generator into a robot manipulator? It shifts the focus from just seeing to proactively predicting.
Precisely. And to do that, they needed to make the video generator produce actual executable actions and to align that visual imagination with a physical trajectory.
So how do you do that? How do you actually get something that makes cool videos to, output physical instructions for a robot arm? Let's get into the architecture.
It's all built around a multi-modal diffusion transformer, a DIT. And the key, the absolute crucial first step, is that it's initialized with the weights of that huge CogVideoX 5B video model.
Let's just pause on that for a second. This isn't just some random generator. They are giving the robot essentially a PhD in real-world physics before it even learns its first task. That scale feels critical.
Oh, it's indispensable, and we'll see the numbers on that later. So once you have that backbone, you feed it two main inputs. First is the language instruction, which gets encoded by a standard T5 text encoder.
And the second input is what the robot is seeing right now, but not as raw pixels.
Correct. The current observation, O, is actually the first frame latent V1. It's been put through a 3D causal VAE encoder.
Okay, that sounds a little dense. Can we break down what first frame latent means for everyone listening?
Sure. So instead of feeding the model millions of raw pixels from the camera, the VAE, the encoder, compresses that frame into a much smaller, more efficient representation. It captures the essential visual information, the objects, their positions, without all the noise. The transformer is working with the essence of the image.
Got it. And then comes the output, which is where that dual prediction thing happens.
Right. It predicts two things at the same time. The first is the action chunk, A, which is a sequence of the next K actions the robot needs to take.
And each action is one of those 7D vectors, which is basically the language of movement for this robot. What are those 7 dimensions telling the arm to do?
So that 7D vector is the command. You have 3 dimensions for translation. That's the XYZ position of the wrist, then 3 for the rotation of the wrist, and the last dimension is just the gripper state. It's binary, so 0 for closed, 1 for open.
Okay, so that's the do this part. What's the second imagine this part of the output?
That's the future frame latents, F. This is the visual imagination. It's the predicted visual content in that same compressed latent form of what the world will look like after the robot executes that action chunk.
So what makes this so different from other models? Is it just that it's all happening in one unified system?
It's the unification, yeah. They use a single DDIT framework trained with a standard DDPM diffusion loss. They basically line up the language tokens, the current visual latent, the action chunk, and the future video latents all into one long sequence. And the model learns to denoise all of them, video, language, and action simultaneously.
So it forces the predicted action and the predicted visual consequence to be coherent.
It has to be coherent. And that leads directly to the paper's most powerful finding. The proof that this imagination is what's driving the robot's success.
This is really the core takeaway. The experiments showed this incredibly strong link. When the predicted video, the imagination, was high quality and looked physically plausible, the action sequence worked.
And when it wasn't, it failed.
Yeah. So the proof is in the pudding. What happens when they just turn off the imagination part? The ablation studies must be pretty stark.
Oh, they're brutal. The full default VideoVLA model gets an 80.4% average success rate. But when they remove the video denoising loss, so the model still predicts the video, but it's not graded on how good it is, the success rate just plummets.
Not far.
Down to 27.0%.
Wow. A drop of over 50 percentage points. That's definitive. It's not a side effect. It's the main mechanism.
Exactly. And if they take video out entirely and just predict actions, it's even worse, 25.5%. It proves the point. The reliable actions emerge because the model is forced to visualize the consequences.
The paper calls the visual prediction task an implicit regularizer for the action space. Could you simplify what that means?
Yeah, think of it like this. To generate a realistic video of a block being picked up, the model has to respect the laws of physics. It can't just have the block teleport or float through the gripper.
Right.
That need to make a plausible video forces the actions that create that video to also be plausible and physically valid. The imagination is basically policing the actions before they even happen.
And they even back this up with visuals, right? The motion similarity analysis.
They did. In Figure 3, they track key points across the imagined video and the real video, and the results are crystal clear. The successful executions had way higher motion similarity between imagination and reality than the failed ones. The robot only does well when its internal plan is accurate.
Okay, so now let's get to the payoff. Generalization. This is the whole point, and the benchmarks really show it delivered.
First, on in-domain tasks, it's top of the class. It got the highest average performance across 12 simulated tasks, beating strong baselines like CogAT and Pi0. So it masters what it's trained on.
But the real test is always novel objects. You can train a robot to pick up a red block 1,000,000 times, but what happens when you give it a wrench?
And this is where VideoVLA really pulls away. In the simulation with 10 unseen objects, it hit that 65.2% average success rate. That's a huge leap in handling physical novelty.
And did this transfer over to the real world? Sim2Real's another huge hurdle?
It did. They used the Real Man robot, fine-tuned it a bit, and it successfully handled all 12 novel objects they threw at it. Different bottles, a screwdriver, a toy duck.
What was the success rate there?
It was 50.6%. Now that might not sound amazing, but you have to compare it to the baseline. OpenVLA only got 9.6% on the same task, so it's a massive, massive improvement.
I mean, just picture that. A robot picking up a screwdriver it's never seen before. That feels like a genuine step forward for robotics being useful in the real world.
It is. But the ultimate stress test, the hardest task, is what they call cross-embodiment skill transfer.
Okay, what does that mean?
It means having Robot A perform a task that it has only ever seen being done by Robot B, a totally different robot with a different body.
Whoa! So it has to learn the general skill, like topple a bottle, from watching one arm do it, and then figure out how to do that same thing with its own completely different mechanical body.
Exactly. And this is where the generative model really flexes its muscles. In simulation, transferring skills from a VideoVLA robot to a Google robot, VideoVLA got a 48.6% success rate. That's over 28 points higher than the next best model. The imagination lets it abstract the skill away from the body.
What kind of skills are we talking about?
Complex stuff like takeout, where it got 93.8% success, and slide 2, where it got 40.0%. It's encoding the general physics of the task, not just one robot's specific movements.
And they got this to work in the real world, too.
They did. The real man robot successfully transferred skills it had only ever seen the VideoVLA do, like topple bottle and white table, and got a 58.0% average success rate. That kind of hardware-agnostic skill transfer is a really big deal.
So let's look at the architectural choices that made this possible.
Yeah.
They did an ablation on the backbone model. Was using a huge model like CogVideoX 5B really necessary?
Oh, absolutely critical. The study is night and day. When they trained the exact same VideoVLA architecture from scratch, it got a terrible 12.6% success rate.
12%.
Yeah. The only reason the main model gets to 80.4% is because it starts with all that pre-trained knowledge from CogVideoX 5B. The general knowledge of how things move and interact, learned from the internet's worth of video, is non-negotiable.
It's all about transferring that existing knowledge. What about the planning horizon? Does imagining further into the future help?
It does, consistently. The model that predicted a longer future 49 frames outgot that 80.4% success. When they shortened the horizon to just 13 frames, the success rate dropped to 75.2%. Longer-term imagination leads to more robust actions.
This all sounds incredible for generalization research. But there's always a trade-off.
Yeah.
What's the big bottleneck for putting VideoVLA to work in the real world right now?
It's speed. Inference speed is the primary limitation, and it's a big one. The model relies on that huge generator and multiple denoising steps for every single action.
How long does that actually take?
About 1.1 seconds per step on a top-of-the-line H100 GPU. That means you're getting a control frequency of maybe 3 hertz.
Wait, 3 hertz, 3 commands a second. That's agonizingly slow for any kind of dynamic environment. That basically disqualifies it for a factory line or a service robot, right?
Yeah.
How do you justify that?
It's a totally fair challenge. The justification is that this paper is about proving the principle. It shows that generation models are a better foundation for generalization. The mechanism works, even if this first implementation is slow. Right now, it's a generalization machine, not a speed machine.
So the path forward is all about cutting down that latency.
Exactly. Future work is already looking at things like model distillation training, a smaller, faster model to mimic the big one, or using one-step denoising techniques to speed things up dramatically.
So wrapping up, what does this all really mean? It feels like VideoVLA offers this compelling new direction for robotics, proving that these huge video generation models can be turned into really effective, generalizable robot policies.
It really reframes what we should be looking for in a foundation model for robotics. By making the robot predict a plausible future, you're forcing it to learn a rich, internal model of physics that goes beyond any one object or robot body. That dual prediction strategy fuses planning and execution. Reliable action just emerges from being able to visualize the consequences.
So if a robot's ability to perform a new, complex task is tied directly to its ability to visualize a physically plausible future, does the key to AGI and robotics lie not in better comprehension, but simply in a better imagination?